Some more about antiderivatives. I want to talk a little bit more about the plus c, and then we're going to see it in action in a couple of times in the next example. There's a lot of cases where we really want and should and expect to be able to find exactly what this function is, but we're never going to be able to find what the antiderivative is just from the data of its derivatives. You're going to have to be given some other kind of data, and we'll see physically in a position velocity acceleration problem in a minute where that might come in a real example. But here, suppose we knew this about our mystery function big F. Its derivative is little f, which is e to the x plus cosine x, and we also know. Suppose we forgot to include. We notice, oh hey, we look back at the book, and we notice that let's say the only thing we directly know about big F is that its value at x equals 0 happens to be 3. We're not given anything else about big F directly. We're given its derivative, and we're giving one value of the function. It's a very common situation, and that will allow us to find out what big F is. We already know it has to be of this special form, and then we can just plug this in and plug in x equals 0 and solve. So we know that 3 is f of 0, and that's going to be e to the 0 plus sine of 0 plus c. Now that's 0, but that's 1. Careful. And so c, you bring the 1 over, you're going to get 3 minus 1 is 2. Okay, so in fact, our final answer for that souped up version of the problem is that our mystery f, big F of x, was e to the x plus sine x, sorry about that, plus 2. That said it has the correct derivative and has the correct value at 0. So that's often called an initial condition. And so we'll see in our more complicated example, I guess we don't need the header anymore, why that would be the case. So let me just do the next example just as a little bit of an elaboration, and then I'm going to show you how secretly it's really a very important kind of physics problem. So let's say find f. I think I got this out of the book a long time ago. Find f given, so I'm going to drop the whole big F little f thing. I wanted to introduce that, but it's not an essential thing. So find mystery function little f. Given that, I'm going to tell you its second derivative. And I'm going to tell you its second derivative is 24x squared plus 2x plus 10. And I'm going to tell you a single value of the mystery function itself, and I'm going to tell you a single value of its first derivative. Okay, so that's interesting. And we'll see why, just purely mathematically, why we're going to need to have this exactly something like this information, and this is exactly going to work as we go to get a unique answer for little f. Okay, so just like second derivatives are first derivatives done twice, we're going to undo that twice. So the first thing is we're not going to try to directly get f. We're going to try to directly get little f prime. That should be some function whose derivative is this one. Okay, still power functions, polynomial is not too bad. This is going to be the antiderivative of x squared. Well, antiderivative of 3x squared is what we started with. That was just x cubed. This is 8 times bigger, so I claim it's going to be 8x cubed. And if you take the derivative of that, 8 times 3 is going to be 24. Okay, and we'll get really systematic about this, but at this point we can still kind of guess. Antiderivative of 2x, pretty easy to do. That's x squared. Antiderivative of an additive constant. Don't think that dies because we're anti-differentiating. The kind of thing whose derivative is a constant is a straight line function. So that's going to be something whose slope is 10, so 10x. But then, of course, plus c. Because at this point, without this information here, I could put anything I want to in, and it's going to work. Something whose derivative is this guy. But that's where we put this in. Oh. If this is known to be true, just even one special value of f prime, that is going to lock down the c. Okay, so now we're going to solve for c. It's a very common process. Take an antiderivative, either simple or complicated using fancy stuff, and then solve for c. And we're just going to plug in. We're going to get minus 3. That's what we get for this side when we plug in x equals 1. And of course here we actually just plug in algebraically 8 plus 1 plus 10 plus c. And so c is minus 3 minus, it's a 19, okay, minus 22. Now, immediately you should go back and say, okay, I never want to call this big C again. I now know what it is. Okay, so that's halfway, but very definite halfway version. Okay, so I'm going to just erase that because it's done its job. Okay. So now I just want to figure out what's the mystery function whose derivative is this. We're going one rung up the ladder, as you will. It's a metaphor I use a lot. Okay, so antiderivative of, let's see, if this was just 4x cubed, it'd be great, because then it would just be x to the fourth. Ah, this is just twice that, and so you get 2x to the fourth. Little contrived so that there's not even any fractions, things like that, but I'm trying to make it, just get at the idea. Well, here, we're gonna have a fraction. The derivative, the antiderivative of x squared, again, the antiderivative of 3x squared was the easy one. That was x cubed. This is 1/3 of that. So you get 1/3 x cubed. Another way to say it is derivative of x cubed would be 3x squared. I need to cancel that out. Again, whenever things are just about constants, either adding or subtracting or multiplying and dividing by constants in calculus, it's easy to do stuff and it's easy to even undo and kind of fudge a calculation. When those things are not constant, you're going to have to do a lot more work to get some more intricate. But here it worked. Antiderivative of 10x, well, that's 5 times 2x, and we just did that one, so that's going to be 5x squared. And again, antiderivative of a constant is just going to be a linear function. And so now here I'm going to almost violate a rule, which is don't use the same letter for different quantities. But that plus c was a very temporary thing, and it's gone. And a very common thing, a little bit loose with our conventions for doing careful math, is to just say, okay, we're going to call that plus c. Now, there will be situations where I don't have this information, and this plus c will stay around as a bit of ambiguity. Then you can't use the same letter for this guy. You use like big C and big D, or C1 and C2, or C0, C1, C2, C3, C4. That happens, and that's important. Just never use the same letter in the same exact expression for different quantities. Please, please, please. Okay, so this is where we'd have to stop if we didn't have this information, but we do. And so when I plug in x equals 5 over here, it should get the same thing as when we plug in x equals 1 over here, and we get 5 as the output. And so that's 2 plus a third plus 5 minus 22 plus c. And so let's see. This is, let's just move, well, let's see. That's going to be minus 20. Oh, that's minus 15. Okay, so then move it over. It's going to be 20 minus 1/3. Okay, or 59 thirds is equal to c. So not pretty, but not incredibly awful. Okay, so now I'm just going to go ahead. You really should rewrite this, but I'm trying to be a little quick. Okay, ta-da! There's our explicit function. So, and this kind of exact procedure happens a lot. So let me tell you. Let me pull back the curtain. Why would we do exactly this kind of problem? Okay, and just there's a lot of pure mathematical places where you would do this. Definitely not only the example I'm about to show you, but for me, the one to focus on is where we're looking at the position, which we often call s, of time. I'm going to change all our x's to time. So it's mystery position of an object given the second derivative of position. Well, what's s double prime? Oh, we usually call that the acceleration. And I'm just going to change all my x's to t's. And this is now, and then what are we given? We're given the acceleration for all future times, or at least for a while, unless for some interval, let's say. Okay. And just given the acceleration, how the velocity changes of some object, that's not quite enough to tell me exactly where it's going to be. But it turns out, if I say at time 1, if it's at position 5, and one other thing, which is, now that first derivative, that's the velocity. If I tell you where it is at some fixed time, say time t equals 1 here, and how fast it's going, right then, but then I don't tell you any more explicit direct information about position and velocity, but instead give you very precise future information for all future times for the acceleration, then I can first figure out what the velocity is as a function of time. I can predict all future velocities. And then doing another antiderivative step, I can predict all future positions. I know where this thing is going to be. And it's the same exact calculation, just different letters. So this is a very, very common thing. We're given acceleration and just a little bit of information directly about position and velocity, and we can figure out future velocities and future positions. I can track this thing and know where it's going to be. And why would I know acceleration information? It's because in sort of basic Newtonian mechanics, we have F equals ma, that acceleration is linked directly to force, and it's fairly common that we might know something about the forces on this object. Now, it often gets more complicated than this, maybe it's still a little simplistic, but this is definitely a key piece of the modern understanding of how the world works, is that there's forces that act on stuff, that tells us accelerations, then doing antiderivatives tell us velocities and positions. It's pretty awesome.